As a starting point for superconductivity study, we started from the London theory. And London theory describes for the electrodynamics, and there is a pairing mechanism does not take into account, and also the pairing mechanism is described from the BCS theory, the microscopic theory of superconductivity. And the London theory only described for the phenomenological description for the paired electrons and perfect conductivity, and as well as the diamagnetic phenomena. But in this case, and I will start from the Ginzburg-Landau theory. And anyway, the Ginzburg-Landau theory is also phenomenological theory, but the different thing between the Ginzburg-Landau theory and the London theory is that in the case that the London theory described the superconducting state as perfect conductivity and perfect diamagnetism in terms of electromagnetic behavior. But in Ginzburg-Landau theory deals with thermodynamic point of view and free energy. And here, chapter 7, it is Ginzburg-Landau theory. Anyway, Ginzburg-Landau theory is widely applied in physics, such as well as the superconductivity and magnetism and ferroelectricity, and various phase transition can be described by the Ginzburg-Landau theory, because Ginzburg-Landau theory itself is the phenomenological theory, and also it is a thermodynamic description, and also it is natural to understand. And anyway, and the thermodynamics is not a microscopic theory, but a phenomenological theory, but it is applied very well in our daily lives. Therefore, the Ginzburg-Landau theory is very fruitful theory in superconductivity. And anyway, the Ginzburg-Landau theory is widely, as I said, that the Ginzburg-Landau theory is widely applied, and also the theory also can apply to the particle physics and the creation of universe and the phase transition, and so many theory can be applied. So many phenomena can be applied by the Ginzburg-Landau theory. The basic idea of the Ginzburg-Landau theory, there is no order parameter. Introduction. And there is no order parameter. What is the order parameter? Order parameter in physics, it is a measure of the state. For example, in daily lives, there is a phase transition from the liquid state to the gaseous state, or the liquid state to a solid state. And for example, there is a freezing condition from the freezing of the water and boiling of water. In this case, the solid state, what is the distinguishable between the solid state and the liquid state? And basically, the distinguishable factor is that the compressibility, because liquid is incompressible and the solid is compressible a little bit, and the gas is compressibility is so high. Therefore, the liquid state and the solid state, the distinguishable parameter can be think about the compressibility, and therefore the compressibility is a kind of order parameter. In the case of magnetism, and magnetism case, spin ordering generates the magnetic moment. In phenomenological means that the measurable quantity is that the magnetization or the magnetic moment. And the magnetic moment in the paramagnetic state or the non-magnetic state, non-magnetic state and the paramagnetic or ferromagnetic, if there is a phase transition from the non-magnetic to the ferromagnetic, and there is a magnetization develops significantly, and therefore the magnetization is an order parameter in magnetism. And therefore, in some cases, the liquid to the vapor and the vaporize of the water is that density. Density is an order parameter, and therefore the order parameter characterizes the phase transition. Therefore, Ginzburg-Landau assumed that there is an order parameter, and the order parameter it is written by the phi, but it is a complex order parameter. Like that, phi equal to phi absolute and exponential I zeta. Zeta is a phase vector. In many cases, order parameter is a real value because it is a measurable quantity. But in quantum mechanics, in quantum mechanics, superelectron state in supernativity is the quantum mechanical behavior. It is supernativity is the macroscopic quantum phenomena. Therefore, in supernativity case, and the order parameter can be think about that the complex number and not a real number. And anyway, in quantum mechanics, there is momentum becomes like or momentum operator like momentum operator. But on the magnetic field, this momentum operator becomes that additional vector potential. Here E star means that the superelectrons on the magnetic field can be write down as the call A. A is a vector potential, and E star is the superelectrons. In BCS theory, the superelectrons is a coupling of two electrons, therefore it is a 2E. It is similar. Can be write down plus minus. Plus means the whole, and minus means the electron carrier. And also, therefore, the free energy. There is a free energy is a function of this order parameter and vector potential. And the vector potential is the applying magnetic field. It is applied external order parameter. Vector potential is the external order parameter, and phi is the internal order parameter. And therefore, and anyway, as I said that what causes the supernating state, and it comes from the Gibbs free energy, and the free energy prefers to the supernating state at a low temperature, and because it is a condensation of electrons and super electrons, if it is Gn means that the normal state free energy, and the supernating state free energy is lower than the normal state free energy in the supernating state. We call it is a TC, and it is we do not know exactly, but if we assume it is natural, think that the supernating state is energetically favorable in supernating state. Yeah, it is very naturally understood. And here, and we will think about it. The order parameter characterize the phase transition in the supernating state. The current is carried by superelectrons, and you saw here superelectronic mass is about 2m because of two electronic coupling. And also the superelectron density is one half carrier density. And also in at TC means that disappearing of the supernating state, and also super electron density equal to 0, and generally, and the super electron density is less than the normal 1/2 normal electron, total number of electrons. And also here, Ginzburg-Landau theory formulated a complex order parameter, and here we say that this is order parameter. We starting from the order parameter. And also here, let's think about that Ginzburg-Landau equation. And the Ginzburg-Landau assumed that close to below Tc in this case superconducting state, the Gibbs free energy density. Here we denote that Gs as a function of phi can be expanded as, and here I will describe for the Gibbs free energy in the superconducting state is that the normal state Gibbs free energy plus it is energy density and the volume integration, and the energy is that the first term is kinetic energy 1/2m star, and also here phi star phi and plus 1/2 mu 0 and b square r minus mu 0 hr dot mr plus a phi square plus 1f b phi to the 4 and higher order term. It is very important, and Gibbs free energy is very important in Ginzburg-Landau. It is Ginzburg-Landau free energy. Here is the A and B. A and B is that functions of temperature, and it is coefficients. It is A and B is a function of temperature, and it is very complicated. It seems to be complicated free energy, but when you see that in detail, it is very easy to understand, because the first term is easy. It is a normal state Gibbs free energy, and in the integration, and this term gives that kinetic energy. It is a kinetic energy under the magnetic field, because we inserted the magnetic vector potential A, and also here it is kinetic energy. Momentum, it is canonical momentum. It is canonical momentum square, because it is complex conjugate, means that complex conjugate it is momentum square of phi square. Phi square, why we use that phi square? It is that order parameter itself is a complex number, and the complex number is not a real measurable quantity. In quantum mechanics, the wave function is complex value, and the wave function square is the real measuring quantity, and which is that which is the density of electrons. Therefore, in this case also, the order parameter itself is not a measurable quantity, but the order parameter square becomes a real number, and the real number can be measurable. Therefore, the first term is the kinetic energy, and the second term is the magnetic field energy. And also here, the third term is that it is a superconducting energy. It means that condensation energy. Because in this case, magnetization and the magnetic field are antiparallel with each other. Therefore, the sign is minus, and it means that the Meissner state. And the magnetization is different from the magnetic applying magnetic field, and it describes for the Meissner state, and also the Meissner state, this field energy is directly related to the condensation energy. And if there is a magnetic flux inside a sample, and it shows that the field energy. And the problem is that this latter term is the Taylor expansion of the order parameter. Order parameter square, Taylor expansion of order parameter square. And also, therefore, you should remember that this Ginzburg-Landau free energy, because it is a starting point from the Ginzburg-Landau equation. And also, important thing is that this Taylor expansion of the order parameter, you should remember this one. And anyway, then it is canonical momentum, and the field energy, and superconducting condensation energy, and it describes for the superconducting state. Here in some cases, in the normal materials, normal material means that the non-superconducting state. In this case, the magnetic field, B field, is that the mu 0 H, and the magnetization equal to 0. Therefore, the field energy term, the field energy 1 over 2 mu 0 B square minus mu 0 H dot M becomes, is this because magnetization is 0, and therefore it is 1/2 mu 0 H square. It is a field energy in superconducting state. And the second perfect conductivity case, is that the internal magnetic field is 0, and the magnetization becomes Meissner state, and totally expels the applying magnetic field. Therefore, the same term, this magnetic field term inside a sample, becomes that it is mu 0 H square. Therefore, the normal state and perfect conductivity has a different state. In equilibrium state, and the superconductor distributes currents in such a way that to minimize the total energy. And here we say that let's assume that this Taylor expansion of the order parameter, and the A has a function of temperature, and here A0 T over Tc minus 1, and also B it is a B0 near Tc, and also A0 and B0 are positive. Below Tc, that's why below Tc, and the A it means that below Tc case, temperature is Tc lower, and At becomes negative because of the A0 is positive, and therefore the order parameter case and A phi square plus 1/2 b phi to the 4, this term, and shows that it is a negative value and b is a positive. And therefore, there is competition between the negative and positive, and the negative stabilizing the free energy, and the positive and the destabilizing the free energy. There is a competition between the A and B constants. And from this Ginzburg-Landau free energy, and let's calculate the Ginzburg-Landau equations. The first one is Ginzburg-Landau free energy, and anyway, the first one is Ginzburg-Landau free energy, and let's denote the second case is Ginzburg-Landau equations. Here, we should determine the order parameter, because order parameter is a real value to characterize the superheating state. Therefore, to determine or characterize, determine the order parameter, and we should minimize the free energy. Here, let's minimize the free energy Gs with respect to phi star by constant phi. And I mean that here, this case, this Taylor expansion of order parameter, this term can be write down as A phi star phi, because it is phi square means that phi star phi in complex number, and plus 1/2 b phi star phi and phi star phi. Therefore, let's assume that the phi is a constant here. Phi is a constant, and the phi star, let's have a derivative and for the free energy. And here, and anyway, this free energy can be write down like this. Let's denote that light down. And anyway, here, in this case, and subtract this term in the outside, then here minus 1 over v h bar square integral dr 1 over 2 m star, and del plus I e star over h bar a phi star, and del minus I e star over h bar a phi, plus 1 over mu 0 p square r minus mu 0 h r dot mr, plus a phi star plus 1/2 b phi star. And also the first Ginzburg-Landau theory, let's denote that the partial Gs, partial phi star should be equal to 0 to minimize the superheating Gibbs free energy with respect to the order parameter. Then, because these other terms in the magnetic field and the magnetization, there is no there is no function of the order parameter. Therefore, we can discard this term. And anyway, in this case, we can write down 1/2 h bar square over 2m star, and here the complex conjugate col plus I e star over h bar a square phi. This is the kinetic energy term, and plus a phi plus 1/2 b phi square phi equal to 0. And this is simply described first Ginzburg-Landau theory. It is first Ginzburg-Landau theory. Then the second Ginzburg-Landau theory is that it is the first Ginzburg-Landau theory is the derivative with respect to the intrinsic order parameter, and also the second Ginzburg-Landau theory is the derivative of the superconducting Gibbs free energy with respect to the applying magnetic field vector potential. Should be 0. And here this is the vector potential is the extrinsic order parameter. Therefore, here this is it gives the second Ginzburg-Landau theory. And let's think about. Let's remind this free energy. Let's remind this free energy, and let's have a derivative with respect to the vector potential. And the first term is that h bar square over 2m star. Let's derive derivative this term, and I e star over h bar and phi star, and del minus I e star over h bar a phi, and let's derivative in the second vector potential, and it is plus h bar square over 2m star, because minus minus becomes plus, and also here call plus del plus I e star over h bar a phi star, and also I e star h bar phi, and plus, anyway, in this case the other term does not have the vector potential, but this term has a vector potential because magnetic field is called A. Therefore, there is a vector potential inside the magnetic field. Therefore, it does not 0, and the 1 over 2 mu 0, and partial A and b square r should be equal to 0. And when you summarize this one, so minus I e star h bar to m star, then the first here the del, this del, phi star del phi minus phi del, because this del operate to the phi star, and phi star, and this phi is independent with this del operator, and also this is this term, and the second term is this one. It is that minus e star square over 2m star vector potential phi square, and there are two terms, 1 2 multiply 2, and plus 1 over e mu 0 partial square b square partial a square 0, because we should calculate this one, because it is that partial b square is that scalar function, and a vector is the vector function. Therefore, it is scalar vector derivative of the scalar function. Therefore, here let's think about that I component. Then in this case, partial AI and b is a different. B is a scalar function. Therefore, b square is a scalar function. Therefore, it is bj. It is different indices should be. Then in this case, it is 2bj partial bj partial ai. It is 2bj partial ai, and b is that call a j component. Then 2bj partial ai epsilon j alpha beta partial x alpha a beta from the permutation symbol representation, and it is that 2bj epsilon j alpha beta and partial x alpha, and this one a beta partial ai is that correct delta I beta. And therefore, it is that 2bj epsilon j alpha beta is that I partial x alpha. In this case, 2 epsilon I alpha j and the partial x alpha bj, then it is alpha j, then it is minus 2 call b, and it is I component. Therefore, this calculation is that the minus 2 call b, and therefore here when we substitute this equation, then it becomes that let's remove this other right hand side. It is that 1 over mu 0 call b, and it is current density because call b is the mu 0 j. Then it is that it is this one, and therefore let's write down like that 2m star I h bar e star phi star delta phi del phi minus phi del phi star minus E star square over m star a phi square. It is the second Ginzburg-Landau equations. It is the second Ginzburg-Landau equation. And anyway, and at present, you do not need to remember this first and second Ginzburg-Landau equation, but you should remember how to derive the first and second Ginzburg-Landau equation, because anyway, you should remember the Ginzburg-Landau free energy. Yeah, you should remember this Ginzburg-Landau free energy. Okay, and then from this Ginzburg-Landau free energy, you can derive then the first Ginzburg-Landau equation and the second Ginzburg-Landau equation. And remember that the second derivative of this one is that minus 2 call bj, and then it is, you can think that you can calculate like this.